frame calls. So this is kind of the most relevant. I mean, this is for me the most kind of relevant, the starting point for making palettes. So calls allow users to interact with your state transition function. In this lecture, you'll learn how to create calls for your palette using frame. Okay, and some of you may have already touched it and played with it, but I'm going to go into more details exactly all the requirements and things that works. Okay. So first, get some terminology out of the way. You've heard from me and from the documentation and stuff the term call, extrinsic, dispatchable, right? These are all different words, and truthfully, I wish we had a little bit better, what is it called, like discipline around just using simple terminology. But practically speaking, these are all the same. These are all, whenever I say your dispatchable isn't working, or I say your call isn't working, or I say you're going to submit an extrinsic, it's kind of in the mind the same thing. But I want to put a sentence which I think is very accurate, which tells you kind of why they're all together. So users submit an extrinsic to the blockchain, which is dispatched to a pallet call, right? So an extrinsic is dispatchable. Dispatchables are sent to calls. That's why they all kind of sound the same, right? They're all kind of there. But this is the exact terminology, right? An extrinsic is a message from outside the blockchain. There's some dispatch logic, which is routing the message to the correct pallet and the correct call. And some call is actually a function which is being called and run. But practically speaking, these are all the same thing, okay? So just in your head, they're all the same, okay? Call definition. So this is an example of a simple call. Am I missing index? No, I have index there. Okay. Okay. This is an example of a simple pallet call. I'll break it down, right? So actually, this is using something different, which I'll talk about. But this is using a call at the top of the pallet, at this impl, rather than for a weight, rather than a weight at each extrinsic. So actually, maybe you could do this in your pallets, and you can avoid having to make a new weight every single time. But I think I talk about both features. But here, you have a call. There's some macros. All of the calls are implemented on top of this impl pallet, right? So these are functions implemented on the struct, okay? And that impl pallet will have on it the pallet call macro attached to it. That will tell it this is where I expect all the calls to be. And then you have a bunch of public functions. They must be public. And each of them are indexed. So it tells you what index these calls are. This indexing is to ensure that if you were to refactor code or move things around, that the actual index of the call is the same. Imagine, for example, you create a multisig, right? And the multisig has a call stored in storage waiting for the approvers to approve, right? If somehow in between that, the runtime gets upgraded and the indexes change, then the call is called, you'll actually call the wrong function. Does that make sense? Because what's stored in storage is an index. It says this palette, this index, this information. If the indexes are changing, it's possible that will get routed to the one you don't expect. So by having this explicit call index, we ensure as much as possible that you can move code around and the indexes will stay the same, that there won't be a breaking change to your transaction encoding, okay? Anyway, that's why we force you to have it. And then you have a public function with inputs. The first input is always the origin, always the origin. And then whatever fields you want, even they can be compact. See, they have the compact scale encoding here. Calls always return a dispatch result or dispatch result with post info, right? And they have some logic, which you've already seen before, like ensure sign, doing stuff, returning possible errors. And then at the very end, if everything's okay, they return okay. That's the basic breakdown of stuff. But practically speaking, this is just a normal Rust function. This is a public function implemented on a struct with some fields and whatever. The macros just force you to do a little bit more in terms of having this origin here, having dispatch result here, having the index here. It's just doing some extra finagling to make sure that you're doing things right. You have a comment? Up here. So that's what I mentioned. I'll talk about that. There's two ways. Okay. So there's just functions implemented on a struct. It's not magic. It's just Rust, okay? You can do this with any kind of function. However, frame magic turns these into dispatchables, right? That the frame magic is actually handling all the routing to actually take a call from outside the world with a transaction and submit it to your function, right? But these public functions are also callable like you had a crate with a public function, right? So if you had another crate that's accessing this thing, you can actually just call the function directly, like a public function, okay? It's just Rust. As I mentioned, every pallet call must start with an origin parameter, which uses the origin for type, which comes from frame system. Okay, so this type is part of the frame system config. Okay, and we'll talk about origin later today. There's another talk on that just right after this, I think. But here's the basics. The basic origin available in frame has these three variants: root, signed, and none. Okay, and again, we have a presentation going deeper into this, but that's the basic one. The one that you all will use. Some of you are already using root. Good. Mostly signed. Okay. Origin checking. Normally, the first thing you do in a call is check the origin, is what you expect. So normally, you're checking things like ensure signed. That becomes a signed message, and that you can extract from it the caller. You want this to be the first thing you do because this check is basically like zero cost, right? It's like basically, you're just checking an enum variant doesn't match. And before you do a bunch of other work in your runtime, you want to just error quickly. Like if the person calling is not what you expect, you want instantly to return an error. You don't want your blockchain to do any more work than it has to. There are, I'm sure, situations where you maybe would do a little bit of work before. But again, when you're building frame calls, you want to error as fast as possible. So do very simple, very lightweight checks at the top, and then more complex storage reads and operations at the bottom, right? Call parameters. Palettes can have additional parameters beyond the origin, allowing you to submit relevant data about what the caller would like to do. All call parameters need to satisfy the parameter trait. So there was a question earlier today. What do I have to do to make it work inside of the parameter? The parameter trait requires codec, encode-like, clone, EQ, debugs, type info, etc. All these things. So if you're creating a custom struct or creating a custom type, you need to make sure that that type implements all these things if you want to use it as a parameter of your call. And Rust is pretty good actually at telling you these things. Like if you try to do something that doesn't have it, it'll say you're missing this trait. So that gives you a signal, oh, I have to implement or derive this trait, okay? Parameter limits. Most everything can be used as a call parameter, even a vec. You do not need to have a bounded vec inside your call parameter. However, there is a limit to the size of a block. Therefore, and of course, transactions are included with all the parameters inside the block. So you cannot have a parameter coming in which is bigger than the size of the block. The biggest call parameter I know of on common use case is the WASM blob. So when you do update code, you must submit as one of the parameters a WASM blob. That's like, up to 4 megabytes, whatever. But I think the blocks inside of Polkadot are currently 5 megabytes. So you can't have any call parameter more than 5 megabytes. And of course, we actually charge a transaction fee based on the size of your bytes. That's in the transaction fee palette. Compact parameters. Parameters that are compact encoded can be used in calls, right? So that's I showed you here, very simple. So if you want to optimize something like a balance, because a balance is a U128, it's kind of a big number of bytes, but you expect that people are transferring often much smaller amounts of data, you can actually put compact here, and when users submit transactions to your blockchain, they'll use a compact encoded type, and then we'll figure it all out magically. Yeah, comment. The runtime, the WASM runtime? Well, we can either increase the limits, or we can just increase the limit, or we can try to reduce the WASM size more, etc. Yeah.
Shawn, question might be silly, but when input parameter is of bounded vector, and this code compiles from outside when a user submits the transaction, and there the size of the parameter is bigger, then that should return an error. When that happens?
One more time, please.
Yeah. So one of the parameter of the extrinsic is a vector type. Suppose vector of U8.
Okay, sure.
Sorry, bounded vector of U8.
Okay.
So say 5 bytes maximum is allowed there, and if a user calls the extrinsic with 6 bytes of data.
Yeah, so it won't even accept it because that doesn't encode correctly. So there'll be an encoding error not even, it won't even get to your call yet. Like at the high level Rust client, it won't even accept that because the bytes are too much bytes.
So error will be coming as encode error.
It will be, yeah, but it won't even be at the runtime level. It'll be before that.
Before that. Makes
Yeah.
sense. Yeah. Thank you.
It's just a thing. I don't know. I mean, it's like it's your choice. It's additional overhead for the UI. We had a question, but I think it was like, why not use compact all the time? I mentioned like, yeah, it's like this is the overhead to the UI, but it's handled. I mean, why not use compact all the time? You know, I honestly, wherever you can use it, you should use it. But like again, it's one of those things that's like it is an additional level of complexity, right? Like it's just one level of explaining more how to encode this thing. So I don't know. I don't think it's a big deal right now if you use it or not in yours. If you want to use it, that's fine too. It really doesn't affect any code you write, and the UI should be able to handle automatically. Okay. Okay. Call logic. So the most relevant part of the call is the call logic. That's just like the body of the function, right? There really is nothing magical happening here. It's just Rust. Again, I want to really mention to you that these calls are just public functions. It's just Rust, right? However, you need to follow one important rule. What is that rule? Thank you. Never panic. Dude, like, I mean, if I see a panic, and we've said it so many times, it's like, doesn't make it, just don't panic. There, you saw the line why you're not allowed to panic, okay? You cannot panic in the runtime. Don't do it. It's not worth it. Rust has all the tools needed for you to handle errors properly. So under no circumstances, save perhaps for storage getting into an irreparably damaged state. Again, let's ignore this. This is must function panic, right? Allowing callers to trigger a panic from a call can allow users to attack your chain by bypassing fees or other costs associated with executing logic on your chain. I said it before, but this is the idea that basically when a user panics, that we unwrap all the stuff, including the fees. Right? It's not a good idea. Instead of panicking, we provide to you the dispatch results. This wonderful type we just talked about, right? So you can handle errors. There's no reason to panic. Just capture, make an error, submit it up to the thing, and you get nice, beautiful error messages to the users too. Okay? Everything will be nice. Again, at any point in your call logic, any point in the stack, that means you're calling other functions, you're calling whatever, you can return an error. And when you do, the transactional storage layers that we talked about will be unwrapped or unwinded, and all the changes will be undone. So at any point, you can return an error. So, don't worry about whatever, just return an error, propagate it up. We will handle that. Your comment, question.
Yeah, question. Can we return a value in the dispatch result or only the unit type?
A value. No, the dispatch error is only.
No, the dispatch result.
Dispatch result is we show that it's either the unit.
So you can return.
You can't return a value. Yeah, the truth is this is a request I've heard about before. Where do you want to return the value to? Like, where does that you ask the question, where do you want it to go?
I mean, if a user executes an extrinsic, maybe he wants to get a value of something back.
But how would he get it back?
He's
submitting a so we have events and errors for that, right? Events and errors are like a way to propagate that data back, right? But it's not like the user isn't a variable where there's an equal sign and there's a function call on the other side, right? The user is submitting a extrinsic to the blockchain is like propagating this into a block. It's like, there's not a clear way to return a number and then have the user assign that to a variable or whatever you're thinking, right? So no. But again, events and errors support that. Maybe this will change. Maybe I don't see a reason why we couldn't do it. I just don't I think actually it could just make giving someone this feature could just make them confused about what they're doing. Does that make sense? You almost want to just stay in this nice comfy, cage of, this is what we return. Okay? But I don't see a reason why not. Yeah, comment on that? Sure, please. Yeah, you can pass the mic over here. Behind you, I think. Behind you.
What you usually would do is to subscribe to the RPC to wait for your result. You would make an extrinsic and then you would subscribe and see whatever change you're looking for.
Right, and then when in JS, when you subscribe, at least with Polkadot.js, you actually also get in the subscription, like the returned result, and you also get all the events associated with that transaction. So you actually get all the information you want kind of packaged to you, but it's through events. Again, events are the way to communicate to your user. Okay, so this is the call return, returning an error, right? So again, very simple. If something goes wrong, you return an error, no problem. And thanks to transactional layers, everything will be reverted. Returning success, once everything is completed successfully, the last line of your palette code is okay. And that's it. And that ensures that the data will be committed to the blockchain. Okay? Call index. It is best practice. It's not even best practice. It's like required now to explicitly label your calls with a call index. This ensures that when you have changes to your palette, it will not lead to breaking changes to transaction format. I gave you just a perfect example. You have some call stored in storage. You plan on executing that call in the future. If the format changes, that call was stored in storage, which is just bytes. It's not it doesn't say balance transfer 500. It says 011011100, and then that gets encoded to then destroy my account. That's bad, right? So you want to ensure that the transaction format stays constant. We have tooling inside of our ecosystem that constantly checks the metadata and checks for transaction breaking changes between upgrades, right? So there's a lot of tooling around this, but the best source of protection is just having explicit indexes, okay?
They can never change them.
No, you can change them, but that is a breaking change, and therefore you need to consider like, okay, if I have a blockchain where I'm storing calls, I might have to do a runtime upgrade. I might have to notify users, notify wallets, notify ledger, right? I think today you just had a presentation about wallets and stuff like that. Like these format changes affects them, right? So you're allowed to break them, but it's like it requires a bunch of steps to make sure your ecosystem can support it. Okay? You want a comment here?
So we have protection against breaking changes in the extrinsics, at least, that as long as index is there, we can move around. What about the structs we define? Do we have protection against that? So in the subsequent upgrade, if we change the field sequence, for example,
Of a struct? No. So there's a talk we have on Friday about migrations and upgrades. And so that like if you change the fields of a struct, you're changing the field of a struct. There's nothing we can do. But you can detect in the metadata that data has changed. So, but for example, we don't have like a field index. The index of a field in a struct is the order of the struct.
Okay, so that will be reflected in the metadata. So as a programmer, runtime developer, we don't have to worry about that.
Yeah.
So we just, as long as we are putting right index, it's safe to upgrade.
It's as long as you have the right index on the call ordering is safe. But other changes you can make to your runtime could break the runtime.
Okay, there are still breakable things.
Right.
Okay.
So imagine I make the call index, I keep it 0, but I just delete all the code in that call. Obviously something is breaking, right?
Yeah.
So the call index is only preventing one specific thing, which is the index of the call. It's the only thing I can protect, right? Yeah.
Okay, thank you.
Yeah. And again, I kind of get the vibe you're going for. Like, how much code can we write to keep you safe? It's like every time we add something to make it safe, you have more of these things you have to add. Like, I mean, how many of you ran into a problem already where you copied an extrinsic and you got an error because you didn't increment the index, right? Yeah. Like, if we just add all these fields everywhere, we're going to make a very safe system, but one that's completely unusable, right? So there's a combination of you being a reasonable developer, understanding the system you're working in, and then also us making some protections that we can make, right? So we saw enough of this problem happening that we said this is worth it, but it's not a big overhead, right?
Cool.
And again, these are all the opinions of Frame. I want to mention this one more time. Let's go back to the idea. I'm teaching you a framework which is very opinionated, has things that we've learned, has styles that we have. If you have your own vision for a runtime framework, not only do I encourage it, I want to see it exist. I want you to build your version of it, whether it be more complex or more simple. All of that is great. You all here in this room are at the cutting edge of what I hope to be a very innovative developer ecosystem, right? I do not want there to be just one framework, but we can teach you our framework, and from this knowledge, you can potentially think of new ideas and ways you can iterate, right? That's why we don't teach you Frame first, we teach you runtime. This course is all about teaching the building blocks here, right? So really take advantage of the ideas you have, and let's extend our ecosystem, right? Yeah. Okay, call encoding. So calls are encoded as 2 bytes. the pallet index and the call index. It's kind of very similar to like the error, right? So we need to know which pallet we're calling and what call we're making the call for. So you could, a call encoding is those two indexes, and of course it includes any other bytes, which are the parameters of the call, right? The pallet index comes from the order of the construct runtime, just like the errors, right? And if changes to this order happen, right, you again will have a transaction format error, right? And we actually, if you look in, we don't require it in the construct runtime, but we allow you to actually directly index these things. So if you go into the Polkadot runtime, you'll actually see explicit ordering of the indexes. But we don't require it because we haven't seen this be a big problem for users. We do require the pallet index because we've seen this happen way too often. It's kind of like, again, we are our control. Each call must also specify a call weight. We'll have, again, a lecture on weights later, but the high-level idea of weights is this, that we need to know in each call how much resources, how much time computation is being used when you make this call, so that we can charge the appropriate fee. If there's a call that says, submit remark, that's a very low fee. If there's a call that says, solve the protein folding problem, that's a very expensive call, right? So the weight describes to the system how much computation is happening here and charges the fee. And again, the runtime does not use gas metering. So unlike a smart contract where gas metering would figure out the weight, we actually do weight measurements ahead of time. This gives us much more performance increase in terms of execution of the code, but at an overhead cost to the developer in order to write weights. Again, we'll talk about this in benchmarking, but this is one of the ways we are able to get that, remember that bar graph, so low, right? But we must include weights. But again, for you all in your palettes, I do not expect weights. You can do weights as an extra, but practically speaking, it's not expected. So just use default, just ignore it. It's something for the production level runtime. So actually, in this original example, I had mentioned, and I should update my template to use it, that you can put the weight at the top of your palette, this palette call, and you can see here there's a weight and there's a weight info. This is somehow able to, I have to look more into this detail actually, but somehow is able to put weights on all of your palettes. But I think the more easy thing to do, and which I've included in your templates, is to just put a weight on top of each extrinsic. So you can have the palette here, it's some weight number. And I think I put like weight default, right? So just do that, ignore it, don't worry about it. It's not a big deal, okay? So it can be done per call. Or it can be done at the top, right? So there are kind of two ways to access this. It's kind of ergonomics for development. It's the same thing. It's all the same thing, okay? Questions about calls? Yes, in the front, let's get the microphone.
If you use the top level weight info, can you also put specific info on each call when it's?
To be honest, I don't know. I haven't mixed and matched, but you can try and see if the compiler errors. I don't know.
Okay.
If you want me to find out, just remind me, and I'll make a test on my own, and I'll tell you. Okay. Yeah.
No, I just wondering in the specification of the weight is included only the computational complexity, or also the storage?
It's both. So the weights are two-dimensional. Weights include a dimension for computation and a dimension for storage, and there might be additional dimensions added later. For example, we don't take into account memory, but that is actually a use. So we are the first that I know of in the blockchain ecosystem to have this multi-dimensional like gas or weights. Yeah.
Okay, thanks.
Yeah. Comment in the front.
So when we put like weight info at the top of the palette instead of putting it on the extrinsics, all the functions, earlier like we used to put weights on the top of the functions and with some numbers on it, right? So now when we put weight info at the top of the palettes, so how does the distribution works like in the number of functions?
I think that this requires a little bit more finagling. So here, weight info, I believe, is a trait which has a bunch of functions which match the function names here. So it's not just like you can put 0 up there. It actually requires you to write some stuff to make it work. So again, I recommend that you don't do this. I recommend that you just do this. the per call. But in the benchmarking lecture, it'll make sense why this one is actually easier for when you actually do proper benchmarking. Okay, but let's save that for, again, I have a whole lecture on weights, and a lot of those questions will come to pass. What I want to show you in this lecture is just the optionality. Keep in your mind, hey, I remember that there was this thing that I could do. Don't actually do this right now. It's not super useful for you at the moment, okay? Just the per call weights, this is what's going to be most simple for you. And that's why, again, I gave it to you in the template this way.
All right, thank you.
Okay. How are we feeling about the calls? Who here has successfully made a new extrinsic? Okay, a few hands. All of you are going to need to do it, right? Every single one of these things has extrinsic. So, okay.